So hello everyone for today's seminar from eSpace. I'm really glad to introduce Dr. Shimrit Maman. She's from the Ben-Gurion University, and her research deals with the application of satellite technologies to environmental challenges and climate change. And today she will make a presentation on single-band nanosat remote sensing, the BGUSAT challenge and opportunities. And I'm really glad to have her today, and I'm really looking forward to learning more about your research. Shimrit, now you can start. Yes, just for information also, the session is recorded, but it's not yet decided whether we'll put on YouTube or not after, so this will be done after. And if you want to ask questions, we kindly ask you also to write in the chat, and then we'll take the questions at the end of the presentation. Thank you. Yeah, Shimrit, now you can start.
Thank you so much, Emmanuel, for this kind introduction. And thank you so much for having me here. It's a great opportunity. This is one of the challenges that were posted by COVID-19. And this is a great opportunity that we could get to know each other better. We were just discussing that before we went on the talk. So my name is Shimrit. I'm from Israel, and I'm from Ben-Gurion University of the Negev. And I am going to discuss today our nano-satellite, which is called BGUSAT. As in you can already understand from the name of the talk, it is a single band nano-satellite, and we do some kind of Earth observations with it. Even though we do have an application of turning around the satellite and looking outwards as well, and I'm going to discuss that later on. So just a bit about us to put you in context where we are from and what we're doing. I'm currently the director for the Earth and Planetary Image Facility in Ben-Gurion University. We are a research laboratory. So what we do is all kinds of multidisciplinary remote sensing related issues. So most of our students, even though they are from different departments and fields, we have physics and geography and electro-optics and electrical engineering. Everybody's doing some kind of different variations and applications on the research of remote sensing. We have our own ground receiving satellite station, and that was designed for BGUSAT especially. So you could understand from that as well that we have our own nano satellite in space. We also have our own meteorological station here inside the university, and a lot of different field equipment that we do like to be on the ground while doing remote sensing. There's several aspects to remote sensing. Some prefer to do just remote sensing and no ground validation or calibration or evaluation. We're the groups that do believe in field work alongside the remote sensing data collection. We are one of 17 laboratories, regional facilities of NASA, a regional planetary image facility. So we do have an MOU with NASA as well. We have a lot of education and outreach and public outreach programs. And I am going to discuss one particular program that we're dealing with today, which is called eSpace, but that would be at the end of the talk. And we also serve as the Israeli Regional Support Office of United Nations, a SPIDER. SPIDER is a space-based information for disaster management and emergency response. That's the acronym. So we are the 25th center in the world for United Nations dealing with those applications as well. Currently, UN SPIDER has 26 centers, regional support offices all over the world. So dealing with remote sensing, I know that most of you are familiar due to the nature of your facility. So I'm going to skip all the introduction of what remote sensing is, but I am going to start off with some kind of overview what's happening in the last years. So basically, we have 61 years of Earth observations, and there is an image here from the Tyros 1 which was taken in like 61 years ago, not so long ago for in human times, but such a long advanced in technology. And when we're looking at those kinds of images and their applications, we're asking what's the big change? What changed in these past years and where are we going? What's the trend nowadays? And we see that basically one of the most apparent things that are happening with this technology is this trend that things are getting smaller and smaller and smaller. And if we were used to really large scaled satellites, now the satellites are getting smaller. And just to put you in scale, there's a human standing in the figure. And we're talking about CubeSats, which are incredibly small. If we look um, for past and current trends in nano and microsatellite applications, we do see that historically most of the missions, okay, most of the missions, and this is 58% of the missions were Earth observations or remote sensing applications. And if we look at the future predictions, and this is we're already there, or this is the current times, but also for the upcoming year, we do see that still 50% of the missions are Earth observations and remote sensing related. So CubeSats with some Earth observation capabilities have been developed in the past years, and yet most of them carry some kind of space weather sensors or modest resolution optical cameras. And some technologies are more appropriate than others for use in CubeSats because of this prone to miniaturization. So we're still not fully in the place we want to be, but we do understand that in the past years, this is the main trend, and this is where we're going. And we have to see the main advantages and disadvantages using this technology. So bearing that in mind, the question that I usually get asked most is, why did Ben-Gurion University take upon itself such a satellite project? Why do you need such kind of missions? And we had several objectives in mind. First of all, we wanted to show some kind of technology capability demonstrations. Basically, we wanted to take a really large satellite, minimize it, and show that we could do the work of a very large satellite. The second objective of going into such an adventure is from the educational point of view. We wanted to allow and teach our students the fundamentals of satellite engineering and project management using hands-on experience, not just theory. And CubeSats are designed and built and taught and tested and launched in a manner that universities could really afford this venture. Last but not least, we wanted to see if we can conduct real science applications with it. And I'm really happy to say at this stage that all these three objectives were positively accomplished and answered. So about our nanosatellite, and that's where we're going. We actually launched our satellite on February 15, 2017 on the PSLV C-37. This is the rocket that you see over here. This is the Polar Satellite Launch Vehicle. It was actually launched from India. And I even do have the video of the launch itself. Is just usually when I show this on Zoom, the streaming is not as well as I wish, because everybody has a different bandwidth of internet. So I'm going to put the link to the video at the end, and you could see it, because one of the most beautiful things on this launch is that it had a sideboard camera, and you could actually see all the satellites being deployed out of the rocket. And it was a really successful launch because it had 104 satellites in total on this rocket, which were all put into orbit and all successful. So that was a very great accomplishment for the PSLV and ISRO as well. So what's on this baby? This is our cute nano satellite. Basically, it's a 3-unit CubeSat. When we talk about CubeSats, we are talking about a measure of 10 by 10 by 10 centimeters. So a 3U CubeSat has three of these units put together. And our our nano satellite is quite unique because it is the only nano satellite currently in space that's a 3U. We do know of another Canadian micro satellite in space with a imager on it, a shortwave infrared imager on it. But this is currently the only nanosatellite in space with a shortwave infrared camera that is operative, and you could download the images, and I'll show you in a bit how. This is a joint venture for the Israeli aerospace industry and the Israeli Space Agency and Ben-Gurion University all together. Most of this satellite, 95% of it was produced here in Israel. So we're talking all the R&D and all the components and even the materials and coatings and everything on it was performed here in Israel. This is not an off-the-shelf product. It wasn't assembled here because we have those applications here as well in Israel. For example, we do have high school children building nano satellites and launching them through the International Space Center, but that's mainly for educational purposes. But this was a bit different. The R&D on it was in a higher level, and we even the camera here was developed by a company, an Israeli company, which is called Microgic, following our scientific requirements. So going into this project, and I was saying we have our own ground satellite receiving station. We had to figure out all the logistics of also communicating with the satellites, which is something you don't think of when you built the lab 20 years ago. It wasn't on our agenda, but luckily, we were able to do that, and we were able to put everything together and build this satellite station. And on the roof of our building, we managed to place the antenna. This is a tracking antenna, a UHF, VHF, and S-band that is able to communicate with our nano satellite. We do have communications with it between effectively once and 4 times a day, depending on the path. And when we talk about telemetry, we actually could hear the satellite. And do you hear that? The older parts, the more mature people in this talk will will remember that this is the old fax sound, but we take that sound and we analyze it and we interpreted it into the telemetry that we can download from the satellite or broadcast to the satellite as well. Currently, we have taken over 6,000 images of BGUSAT worldwide. And this is according to the scientific demands of the different researchers working on the satellite. I could tell you that this is a really small satellite, but it kept us very busy here in Ben-Gurion. We had over 30 groups working on this small satellite from this different aspects. Now, I do focus my talk on remote sensing because this is what I do, but there were a lot of other applications using this nano satellite, of course. So some of the applications that we did that we were able to achieve using the satellite is everything that is connected to climate and meteorological research. And if it either if it's cloud coverage or storm observations or CO2 concentrations, in this specific wavelength, it's a single band, but in the specific wavelength, which varies between 1.55 to 1.7 micrometers, uh, it's a great band to differentiate between clouds and snow and determine some kind of soil moisture and see the earth glow. And here on the left image, you could see how the satellite passes over Israel. And because of its low earth orbit, it does travel at a speed of 7.5 kilometers per second. It's really quick, but you could see how it passes, and you could see everything, including, if you look really well, you could even differentiate between the Israeli and Egypt border just by a quick look. And on the right, we have Israel, both on a day that is with no clouds and a day that is a storm. That shows you just an example of two things. First of all, how we could study storms over a certain area and see the cloud difference. And the thing that you could really see, and this is not trivial for such a small satellite, is the attitude control on the satellite, because basically you see the satellite making such a maneuver and shooting as it goes, not just by Nadir in its applications. So that's another application that was put on the satellite, and for a 3U nanosatellite to have an attitude control system that is so effective and allows us to control the satellite so nicely, it's a great achievement. So going back to the remote sensing applications, this slide is updated for 2018, but the numbers haven't changed dramatically. If we're talking about the overall satellites in orbit versus the active satellites in orbit, we see that the numbers that we're talking about is already measured in thousands. If we narrow it down to Earth observation satellites, we are talking about something around 650 Earth observing satellites. And if we want to extract the number of nanosatellites that have this shortwave infrared sensor on them, then we narrow it down to about 11 active sensors, because even though some of the sensors of the satellites do have such a sensor on board, sometimes that sensor does not work, or it's not always fully operational, or it shoots on demand. It depends on the sensor itself. And of course, it has a great variability between its spectral and spatial properties. But if we take the nanosatellites that are now in space for Earth observations purposes, and most of them are of a company called Planet. You must have heard of them. So we see that currently BGUSAT is the only proper CubeSat that we're talking about, the 3U shortwave infrared sensor that has an imaging capability in such a small setup. So we're very proud of that as well. Starting off with that, with this application and trying to learn the properties, the first thing to do was to review the current sensor and the current sensors that are available for Earth observation missions and that have this shortwave infrared sensor on board them. And as I said, none of them are fully operative. So that's another issue to deal with. But from our point of view, what was interesting the most is to compare the different sensors, because usually when a satellite is when a satellite is launched into space, In the past years, they the the sorry, the objective is not to send a single band into space. Even though this was fully initially this was done in the past, and this is how we started off, and we know that you could extract a lot of data. It's not the desired situation, and you could see here that the different satellites do have other spectral bands as well, okay, depending on the satellite. And BGUSAT is the second satellite over here on the list, but we were looking for the same wavelength in order to compare. And the second thing that we were looking is for some kind of a similar spatial resolution in order for us to extract the information we did. And the thing is that we started off by cross collaboration just to study our own satellites' properties and how it works and how it operates in comparison to different satellites. And by doing that, we do have a very large database now with different satellites at different wavelengths and different spatial resolutions, as you could see here. Uh, and for example, I'm just gonna, this is a really, this is a really short example of how just by a visual interpretation, we could look at images from NOAA. In this case, it's NOAA 16. And this image was taken, we did look for a similar month, but this is a very old image of NOAA from the month of May 2003. And the BGUSAT images was taken on May 10th in 2017. Now, just for the sake of comparison, I usually ask the audience which one do you think is BGUSAT and which one is NOAA. And when a lecturer does that, it usually just wants you to show that the better results are of the satellite he's using. So, so BGUSAT is the image on the left, and this is the NOAA. It's the same spectral band, but it has a coarser um, spatial resolution. Now, the thing is that even though it's in a higher orbit, when you take the results of a satellite that is 10 times, 20 times, 30 times bigger than your satellite, then wanting to achieve this technology demonstration, it works. And comparing it to very large satellites in a different and higher orbit, and getting the same results from a lower orbit at a lower cost with higher spatial resolution, the sense of a technology demonstration is achieved. Now, as for the ongoing research of what we do, so there's a lot of things that we could use BGUSAT, especially because of its specific band and wavelength that it operates in. One of the things is examining CO2 concentrations in different areas. And another example is this earth glow, what we call the air glow or the earth glow. And this is a thin layer of molecules that excite in this specific band, and we're able to detect that from space. And we do have preliminary results for this case study as well. This was achieved also with Professor Colin Price from the University of Tel Aviv. So we have groups from Israel and Ben-Gurion and Tel Aviv working with German groups in DLR on this specific topic over Germany. And the thing is that it's very nice to have this ability to control your own satellite and operate it also at night times and see the specific excitation of such oxygen molecules in this specific band. So that is also a great sense of achievement. Um, One of the challenges, we did call this talk opportunities and challenges. So one of the challenges and opportunity this satellite poses to us is the ability to enhance and the temporal resolution of geo missions because of its small size and because of its repeatedness. We could get a certain area photographed in a great temporal resolution. For example, if Landsat takes images every 16 days, then we could achieve this. We could achieve uh, an area to be imaged every 1 to 4 days. That's the temporal resolution we could achieve. And I'm saying 1 to 4 days because, first of all, it's a single satellite, it's not a constellation, even though we're hoping to get there. But sometimes the orbit itself is in such an angle that even though we have that attitude control ability, it's not the ideal conditions to take the image. So we do have to wait for the most appropriate opportunity. So that varies in about 1 to 4 days. And the second thing is that combining that temporal resolution with the spatial resolution of low missions enables us to get higher and more reliable results in a really low cost. So that was the challenges and the opportunities. And what we're working on is actually trying to apply single band applications. For example, examining the spectral coverage of a certain substitute with the temporal coverage, okay? And this could be done with a one band change detection, taking these single images taken at different times and just examining the difference. But we're also trying to learn how we could use this one band for more spatial applications, even if we have just one image over a certain area. And of course, this has been shown before, but not with this specific bandwidth, and not with the applications that we are looking for. So one example is for this application, and this is demonstrated on Landsat 5. Um, this is demonstrated. Sorry, this is demonstrated on Landsat 5 because one of the things we're trying to capture is flash floods. I said that that this wavelength is sensitive to soil moisture. And in arid environments, we are very concerned about flash floods and about the overall environment and soil moisture of the area. The thing is that every time we try to shoot after a flash flood in this specific area, and this is the southern part of Israel, uh, it's either we had no flash floods and then we couldn't show it, this proof of concept, or that the satellite did not pass on the timing that we wanted it to shoot in order to achieve these results. But we do have now images that show that kind of capabilities, but I just didn't have the time to put this on the presentation. So what we did is we took this Landsat 5 images from 2009 and 2010, before and after a flash flood. And you could see how even though it's a single band satellite, we could play with the band combination in order to highlight a certain phenomena. In this case, it's a shortwave infrared, and everything that is highlighted in pink for that matter is increased soil moisture. Okay, and the same thing was done in the Yotvata region. This is, again, a different kind of, a different region, but it shows the same application. So when we are talking about different satellites and comparing it to them, we do have to overcome all the different properties of the different sensors. For example, go back to the table, remember the table that I showed you. everybody has a different sense of a different ability of sensing in spectral, spatial, and temporal resolutions, and radiometric resolutions as well, of course. But when we take these properties and we wanted to compare them, we wanted to see where is that information, um, where is the information getting lost. And of course, when we're comparing different scales of spatial resolutions, that data has a lot of variability. For example, on the right, it's a BGUSAT image, okay, and the enlarged and the enlarged inset is in blue from BGUSAT, and on the left is a Landsat image, Landsat 8 image, and you could see this is both the same area of the northern part of Israel, the Sea of Galilee, and one of the hard things to detect is actually the edge detection, because while you could see very nicely the lake and how it and where the borders are, and even the agricultural fields over here, it's very hard to detect that in the coarser spatial resolution. So in order to overcome that, we are developing now an innovative methodology based on super resolution that takes both a single band image and a single image, and uses different kind of machine learning and AI for that matter. But we're also using other higher spatial resolution images such as Landsat in order to train our images and to enhance artificially the spatial resolution for those images as well. Now, when you work with a new satellite and you have different groups studying it, one of the groups that we worked with was the um, computation group and the software development. And what they came up with is the BGU image browser. So if you go to Google and you want to play around with our images, they're all available. We already uploaded, I think, 1,500 images that you could download from all places on Earth. If you're interested in working with the satellite images, there is a short registration process just to see. We do want to understand who is using our data, and there are areas that have different clusters, um, because some areas are photographs more than others, of course. And you could download the data and work with it. You have the data that you could work with. So that's another example of how we could integrate students even if they're not interested in directly in space sciences, but there are so many things that are needed in such a satellite project that it gives an opportunity for all fields to fit in. So the big questions and the ongoing research that we're dealing with today is, apart from everything I showed already, is the comparison to existing satellites. We did that with MODIS and Landsat and NOAA, but it's still ongoing, not only with the similar spatial resolution imagery, but also with the higher spatial resolution imagery. And we are using most of the images to do some kind of change detection in arid environments before and after rainy seasons, when the main questions that did guide us is what is the information that could be derived from a 600 meter per pixel spatial resolution, uh, and what could we see, if it's large valleys, if it's playas, if it's alluvial fens. And because a lot of these applications are already well established, it makes it easier. So this technology demonstration was even more trivial to us. I would add and say that we are currently working on our next nano-satellite, which is called NegevSat. And NegevSat is going to be bit larger in size. We are aiming for a 6U nano-satellite. And on board that satellite is going to be this system that you could see over here now. This is a hyperspectral camera that is already reduced in size to half a cube. Okay, so it's half the unit is just the camera, but we're very happy with the application as well. There are groups working both on the optics and both on the applications from the point of compressive sensing on board this nano satellite. So that's our next mission, and this is where we're aiming. But overall, if we take the Ben-Gurion University satellite projects, then I said we have so many different applications with them that include the attitude determination and control and everything that is attributed to that, as well as the onboard software and simulators. We also have a new laboratory in Ben-Gurion University that does onboard processing for nanosatellites, and they base their approach on behavioral programming. So that's an old methodology from the software point of view, and that's a different approach that is used nowadays on satellites. So the main questions that we are left with is more philosophical questions. Is remote sensing the next generation? Is this the future of Earth observation? And could CubeSats by themselves do world-class Earth scientists? And I could definitely answer that and say absolutely yes. And should CubeSat stay primarily focused on educating students in universities? And this is a great review that was already taken in 2012. I just can't remember the name. And what are the different capabilities that are currently under development, or what capabilities have already been demonstrated? And we see that we have more emerging technologies that are overcoming these limitations from the CubeSat's point of view. And even though we have a lot of applications that are not currently feasible, we do see that there's a lot of scientific applications that could be implemented, even though there is a lot of applications that are affected by these limitations, such as the spatial resolution or the single band and nanosatellites. So taking the overall talk and understanding what we did and where we're going, I would just like to sum up with the mission patch, because every satellite has its own mission patch. So we came up with ours as well. So this is the head of Prime Minister Ben-Gurion. He was the first Prime Minister of Israel, and that's also the name of the university. And this is um, the color is orange because looking from space to the Negev region where the university is situated, this is a region that is mostly covered by less soil. So that's the color we usually see. And this application of the satellite is looking over the Mediterranean. Okay, and this is Israel over the Mediterranean. And we did want to highlight two things: the peaceful applications and scientific applications of the satellite, studying the atmosphere and climate change issues that bring us all together eventually. This is and you also have here very symbolically, and this wasn't intended, it just came out this way. This is the constellation Dove that is mostly apparent over Israel in the launch of the launch was in the month of February, and that's the constellation seen best. So we found it very symbolic that the constellation Dove symbolizing peace and these peaceful applications coming all together in a joint project. So we had to insert that into our patch as well. So I am going to stop this presentation now. I do see that there is two, there, okay, no. I am going to move to a different presentation because Emmanuel did ask me to talk about the second project that I'm going to just um, present in a brief, and that's the She Space project. Over here, just a second, I'm just going to share my presentation with you. Okay, here. So, so this is the She Space project. The She Space project is an educational outreach program that we came up with. And this is a program that is designed for high school girls. And as you could see from our beautiful logo, this project is already international and is currently appearing in 8 countries. So the thing is that we started off this project. I'm sorry. We started off this project with the motivation of looking around and seeing that in the academia, as we go, if we start off at the bachelor and master's programs, we see that we do have some kind of equity, or even we actually in Israel have a more female dominated body of students in the master and bachelor's um, a point in time. When you go up to your PhD, you get a distribution of 50-50. But the troubling thing is that when you go up the academic ladder, you just see women disappearing from the VL. So we wanted to target that, and understanding that at this stage that female students enter universities, it's too late to target that issue, this gender leaky pipeline. We started this program in high school, and this program is actually designed to to meet the different learning styles and motivational needs of female students and high school students. And it uses active project-based learning in the field of remote sensing and Earth observation, with a combination of climate change in order to confront that problem. So basically, what we do in this problem in this program is that we have girls from around the globe working on various scientific questions of climate change using space applications and different sensors. When our demand from the girls is that each group uses its own local satellites, and that way we keep and maintain the national view. And they do have some kind of global perspective once they understand that everything that happens around them, or something that happens in Brazil, affects the girls in Germany. So they do get that sense of achievement of how climate change and how everybody is connected. So having said that, we started off this program in 2018 only in Israel, and 2019 we already had Germany and Brazil and United States join us uh, in an active networking setting, that the girls come and conduct their own research in our labs, and act as a simulate a research team around the world. And this year, this also expanded to Spain and Togo and Peru and South Korea. So we have more girls coming in the program, working on different kind of applications of remote sensing aspects, and operating satellites in each facility, and exchanging the results and talking to each other. We do believe that we don't have to necessarily target the gender bias or the leaky pipeline by just talking about it. We decided to try a different approach, which is leading by example. So we do not have any lessons plans that deal with this troubling matter. We just show them what they could become by working with us. So they do have a very high sense of achievement once they leave the program. So, so that's what I wanted to share with you today. And I would be more than happy to take any questions now if you have anything regarding the program or our satellite. Um, and
Yeah. Thank you very much for this extensive presentation. It was really interesting to learn more. As we are not so big crowd, if I don't know if someone has a question and want to jump in, uh, or if you guys are too shy, I can ask a, a question also. Is that I was wondering also if you had plans to send another satellites, another nanosatellite, and if yes, would you keep the same type of payload, or would you want also to explore maybe other uh, uh, payload or the technologies?
okay, so that's the second nanosatellite. What we're working on currently is the Negev sat, and that's our next mission. And the payload is a hyperspectral sensor. That's what we're working on currently.
I see a question here. So thanking you for the talk and asking what is the orbital altitude of the BGUSAT?
So currently it's around 500 kilometers,
Mm-hmm.
and that's its variation, and it declines with the years. So it started off at 510, and we're currently around 500 kilometers above ground.
So I would jump on that. What is the expected lifetime also of the satellite?
I have to be completely honest. We did not think it would survive this long.
You didn't think what?
We didn't think it would be still operative till
Yeah.
now. We when we started off, we said, okay, if it's gonna last for 3 months and take 30 images, we're gonna be so happy. We did what that's what we designed it for. That's what we said, and we would have been extremely happy. We're
Mm-mm.
in a situation now that we're already 4 and 3 months after it was launched. 4 years and 3 months after it
Mm-mm.
was launched, it's taken already 6,000 images. We already have 6,000 images, and it's still operating. So every morning that I come to the lab and I see the message on the screen from BGUSAT to BGU, I'm very very happy. But we're extremely happy with everything that happens on it.
Mm-mm. Um, then I have a follow-up question in the chat. So uh, I would like to know your perspective on exploring synergies of data by LEO nanosatellites constellation, because that approach would be more valuable for extracting atmospheric and surface information.
Yeah, that's true. I do my perspective. It's true. I would prefer to have a satellite constellation, of course, but everybody has their own limitations. In our case, it was budget limitations. That's the only thing we were able to send at the time. And of course, that a constellation will achieve much better results and will allow us to get more valuable information for research from that point of view. That's also my point of view. But these are limitations of what we were able to achieve at a certain time.
Okay, thank you very much. There's a question asking if you're exploring, considering sustainability perspective in the development of your new satellite.
I did not deal with that, but that's a really good question. I do. This is something that I do have to examine more.
Mm-mm.
And
Yeah,
thank you
it's
for
linked
that.
with the new space sustainability rating being
Yeah, of
developed.
course.
So,
It's a great question, but I really did not take any, I did not discuss that yet and we did not examine that.
oh, now people are getting warm and we are getting more
Yeah,
questions.
you could also turn on your camera and talk to me. I would feel so much more comfortable.
Yeah, I think it's okay if you guys, the next one, Alexandre, if you want to talk, or I can also read. I don't know. I, yeah,
Hi, I think I've unmuted now.
yeah, we can hear you well.
Hi, thank you for the presentation. I was wondering about the orbit of the satellite and how did you choose it? And do you have to make trade-off with the sensor itself? And I know some Earth-orbiting satellites are using synchronous orbits to get the best illumination. I don't know if it's the same with the sensor you have.
Yeah, it is. We do have a sun-synchronic orbit, a polar orbit. The inclination is 98 degrees, and this was part of the a critical design review that we requested as following all the talks with the scientists and all the different groups that do use the satellite worldwide, not only in Israel.
Thank you very much.
You're welcome.
There was also the questions with including also the trade-off with the launcher available. Was that also a driver in choosing your
We were
orbit?
actually, I have to be completely honest again, and it was a piggyback ride. We looked for the first available space, and we just got a ride to space. So that was the most available taxi that that just stopped.
That's good. If I may also, I take the advantage of moderating and asking questions.
Absolutely.
We also have at EPFL a student project aiming also at launching a nano-satellite, also 3U, for Earth observation purposes with a mass spectrometer as a payload. My question is, but with its first, like with student projects, also considering how many students did work on this on this mission, and how also did you tackle the fact that with students they are changing like every year or so, and how did you manage this aspect?
Well, that's those are excellent questions. So first of all, I have to say that we had a lot. I said 30 research groups, and I meant 30 research groups. And these are everybody took some kind of different aspect in the satellite design and building and testing and operating, because we had the physics working on both the electro optics and the thermal coatings and all those aspects. And we had the mechanical engineers working on different aspects of the robotics, or even just trying to figure out how to deploy it from the rocket outside. So we had several projects working on that. So every time I give an example of a project, we're talking about 4 or 5 students working on that. So we had a very large number working on that project. We even had students from the business school here in Ben-Gurion working on the design and evaluation of how to manage a satellite project, because this is guidelines that everybody needs, but not everybody has the great fortune of conducting such a mission. Now, changing students is a really great problem, but because we did this along with the industry, so every time we had a student changing, it was always supported by someone from the industry or from the academy. It's either an academic staff member or from the IAI, that these people did not change, and they were always key players. So we did manage to overcome that. And having the knowledge well established and well focused, that was the main pinpoint. This was the main mission in our lab, because we just managed the whole teams all together, so everything came back to us, and we were always the center around us. around that. Now, I have to say that from my personal perspective, that took off a lot of time from my personal research because I had to deal with so many different aspects that weren't not my field of expertise. And I found myself so many times climbing on the roof and fixing the antenna just because I was the only person available at the time to do that, or it's just on the top of my building or things like that. So it did divert a lot of research time towards management time, but it turned out great. Looking back, it turned out great.
Yes. So is there, maybe we have time to take one last question in the audience? Don't be shy. So I guess people, no more question. So yeah, I think we can conclude here. Thank you very much, Shimrit, for this presentation, telling us about the development of your satellite and the applications. It was really impressive to see the difference between the NOAA pictures and yours. So congratulations of this great achievement. And we are really looking forward, working with you also maybe on the She Space program.
Likewise,
And
thank you for
exactly,
having me, and we're waiting for you for next week.
exactly, and
Next year, I'm sorry.
next year, yes,
Yeah.
next week. And yeah, so thank you so much. And if anyone has other questions, I'm sure they can reach out to you, I guess, if you agree.
Yeah, absolutely. You could
Mm,
email me. That's the best way. It takes me some time to answer because I receive a lot of emails a day. But I just want to put down the PSLV video
Ah,
for
yeah,
you
the
to see.
video indeed, yeah.
Yeah, I just want to see. I'm just gonna put the video just a second in the chat. Okay. So you could see that in your free time, because every time I try to,
PSL VC37 with the Cartosat 2 series
Oh, we hear it. So
yeah,
three
it started
co-passenger
working on my,
nanosatellites lifted off.
so we'll look at this then after.
yeah.
That's nice. Yeah, perfect.
Okay, great. So thank
Thank
you
you
so
so
much for
much.
having
Yeah,
me, and hopefully next time we meet, it would be in person.
I hope so. Yeah. Now it's time to meet in person. Thank
Absolutely.
you, everyone. Have a nice day. And next seminar will be end of June and to finish this semester. So keep connected to have the announcement. Thank you, everyone. Have a nice day.